This problem, number 4, is all about determinant properties. So it says, you may notice that a matrix A1 and A3 are obtained from A by changing only one column. We'll look at that in a minute. The first thing is determine the determinant of matrix A by expansion on the row or column of least computation. The one with least computation, notice these are 4x4s. We have to use cofactor expansion. So we want to use the one that has the most zeros. So I'm going to use row 3 here. So plus, minus, plus, minus. Okay, so I have minus 2, and then my remaining values would be 0, 0, 2, and then 2, 2, negative 3, and negative 3, negative 1, 2. You can find any determinant, your determinant for that 3x3 any way you want. I will also use cofactor expansion on column 1, or row 1, because it also has the most zeros. Modified fish method will also work just fine. So it's negative 2 times 2, now my determinant, so plus, minus, plus, so that's a plus, 2, negative 3, 2, negative 1. So it's going to be a negative 2 times negative 2 plus 6, or negative 2 minus negative 6. So negative 4 times 4, negative 16. There we go. There's my determinant of A. So now I go ahead and look at the next one. Using the determinant properties without expansion, so that means do not do it manually, find the determinant of A1 and the determinant of A3. Which means now we need to find the relationship between A and A1 or some side of determinant properties. There's various properties that you have. Write them down on your sheet of paper. If we look at this matrix versus this matrix here, notice these numbers are the same, these numbers are the same, these ones are the same, these ones are the same, so which means column 1 changes. And if I look at this, it looks like column 1 is now this one multiplied by negative 3. So this goes to negative 6, this goes to negative 3, this goes to positive 6, and this goes to 0, which means A1 is equal to A, where column 1 is multiplied by a constant. Therefore, my determinant of A1 is going to be 3 times the determinant of A, or 3 times negative 16, or negative 3, sorry, negative 3 multiplied by A. 3 times negative 16 is 30 plus 12, 30 plus 18, which is 48. There we go. There's my determinant of A1. Now I need to go ahead and find the determinant of A3. So if I look at A3, these numbers are the same, these numbers are the same, these numbers are the same, these numbers are the same. Okay, so those ones are the same, which means only column 1 is changed, or 3 is changed. But there's not a relationship between this column and that one, so I need to find some other relationship inside of this. Notice this column here is the same as this column, so that means these two ones are the same, just multiplied by negative 3. Okay, if you have two columns that are the same or constant multiples of each other, your determinant is 0. So for A3, column 1 and column 3 are multiples of each other. Therefore, your determinant of A3 is equal to 0. Okay, and then it asks which of the matrices are invertible. So A1 and A are invertible. A3 is not invertible. Okay, so if you have a big matrix that deals with determinants, you're dealing with cofactor expansion, but also look for any shortcuts that might allow you to apply determinant properties. Okay, so I did 1, I did 2, now I need to go ahead and find the determinant properties, using the determinant properties to find 2A1, or 2 times A inverse, A times A1, and 3A times A1. Okay. So there's a couple things here in terms of order of operations, figuring out all of that fun stuff. So the determinant of 2A inverse. So I know the determinant of A inverse is going to be 1 over negative 16. If I multiply this matrix by 2, I'm multiplying each row by 2, or each column by 2. So whatever A inverse looks like, it's going to be a 4 by 4. I'm multiplying this row by 2. So that means if I multiply one row by 2, I have to multiply this by 2. If I multiply the second row by 2, I'm also multiplying it by 2. If I multiply this row by 2, another one, this one, another one. So my answer here is going to be 1 over 16 times 16, or negative 1. If I have, the next one is A times A inverse. If I do this, then I can go ahead, it's just going to be determinant of A times A inverse, which is going to be negative 1 times, nope, is going to be negative 16 times negative 1 over 16, or 1. Oh, I'm reading that wrong. It's not A inverse, it's A sub 1. Oh my goodness, I'm reading both of these wrong. If you end up reading something incorrectly, that's fine. That's fine. Go ahead, fix it. Even if you use the wrong matrix, but you still demonstrate the correct properties, you're not going to lose that many points. Okay? But we should read things carefully. So, 2A1 inverse. Same principle applies, I just had the wrong determinant. The determinant of A1 inverse is going to be 1 over 48. If I multiplied that matrix by 2, I'm multiplying same thing, row 1 by 2, row 2 by 2, row 3 by 2, row 4 by 2. So it's going to be multiplied by 16. Same idea, just incorrect. So here it's going to be 1/3. If I go ahead and I do A times the determinant of A1, it's going to be the determinant of A, determinant of A1. So it's going to be negative 16 times 48. I wouldn't necessarily expect you to do that multiplication in your head. It is negative 768. If you have a calculator, non-programmable, calculate it. If you do not, then just leave it like this. It's not the end of the world. And then I have 3A times A1, or A inverse. So now this one is just A inverse. Okay, so if I just do A times A inverse, it's going to be negative 16 times 1 over negative 16. So that one there is just going to be 1. If I do 3 times that matrix, I'm going to do this one times 3, this one times 3, this one times 3, this one times 3. So it's going to be multiplied by 3 times 3 times 3 times 3. This is equal to 27 times 3, or 9 times 9 equal 81. Once again, if you can't do that mental math, then get it as simplified as possible, as far as you can go, if you do not have a calculator. If you do not have a calculator, that's fine. You should be able to do all of the math, really. This one's a little bit big, but this should be manageable. Okay, and there we go. There's our answer for problem 4.